All right, so in this video, we're going to be looking at finding things like the domain and range, horizontal and vertical asymptotes, any slant or oblique asymptotes if they exist, x and y intercepts, all in the service of trying to graph a rational function. Now, in this particular case, we're dealing with actually a special case in which in this denominator, it can never be 0. So this is not x squared minus 64, which we could factor, and then we would end up with a whole. No, this one is never 0 because it's a sum of squares. And so the domain is going to be all real numbers. An interval notation, negative infinity to infinity. Now, we can start finding other things like the x and the y intercept. So the y-intercept is when x equals 0. And so if I plug that in, r of 0 is going to be equal to 8 over 64, which is 1/8. So that point is going to be 0, 1/8. So that is going to already tell me that this is sort of a small scale in the y direction. It's not going to be on the standard window. It might be difficult to actually see what's going on. So you may need to shrink the y coordinates. If you're using your TI calculator, you might want to try using something like Zoom Fit. Set your x coordinates, and then it'll adjust the y coordinates so that you can see the graph on the whole screen. Now, the x-intercept is going to be when we set the whole thing equal to 0. And for a rational function, it's when the numerator is equal to 0. So in this case, x plus 8 equals 0. So there will be an intercept at -8. And then we already said there's no vertical asymptotes because there are no holes in the domain. The denominator is perfectly fine. It's never 0. But what about the horizontal or oblique asymptotes? Here, the denominator is a higher degree than the numerator. And so the horizontal asymptote is y equals 0. So let's sketch, and then we'll verify in Desmos. So we've got our axes. Now we know that we have a 0 at -8. 1, 2, 3, 4, 5, 6, 7, 8. So we have to go through this point over here. We also know that we have a horizontal asymptote that we have to approach, but we can cross it nearby if we need to. We also know that we have a y-intercept. I'm going to put it here because it's 1/8. It's only 1/8 high, but we'll just, again, think about our y range of 1 is like up here. It's a very small vertically height graph because our denominator is so big. So we know we have to go through that point. And then on either side of these, we have to approach the horizontal asymptote. So what that tells me is that on this side of the graph, it may or may not still be increasing at this point, but it can't really do much else except eventually go down to the asymptote. It could be going this way. It's possible the peak is over here without plotting some additional points, but sooner or later, it's going to have to approach the asymptote on the right side. And then over here, we know it has to go through this point. It's not a degree 2, it's not a multiplicity 2, it's not repeated in the numerator. So it has to go through this point x equals 8, but x equals -8, but then it has to come back and approach the asymptote. So it's not going to cross the asymptote again. This is the only place where it will cross the x-axis, but it has to go through it. So there's probably some sort of minimum over here before it comes back up and then approaches the asymptote again. So let us go look at our graph from Desmos and find out how well we did. And so we end up with this. Here's our intercept, that's this guy. Here's our y-intercept, that's here. And again, there is some peak over here someplace, but it's decreasing now and heading back off to 0. You can see there's a small gap opening up here, but if you keep sliding the graph over, you do eventually find there is a very small minimum over here. And this does eventually merge back in with the x-axis. All right, so let's look at another example. So let's try our new function to be x minus 3 divided by x squared minus 9. And this is sort of a more traditional situation where we do, in fact, have a difference of squares in the denominator, and therefore the denominator can be 0, and we do have wholes. So where are the vertical asymptotes? So potentially at 3 and -3, but if we factor the denominator completely, what we see is that we actually have a hole So our factors of x minus 3 are going to cancel, and this actually is going to, except for the point x equals 3, this is going to look more like this expression. So the holes in the domain do not go away. So the domain is going to be negative infinity to -3, skipping over -3, -3 to 3, and then skipping over 3 to infinity. So the domain, both of those factors in the denominator cause the function to be undefined. And so they have to both come out. But the factor that cancels is a hole at x equals 3, and the remaining factor is the vertical asymptote at x equals -3. So there is one vertical asymptote and one hole. Now we want to find the horizontal asymptote. Since these are the same degree, the numerator and the denominator are the same degree. So divide the leading terms to obtain the horizontal asymptote. So that'll be HA is y equals x over x, which is 1. Now, if the numerator is a higher degree, then you would need to do long division to obtain a slant asymptote or an oblique asymptote. So just be aware, you actually have to do the long division in that scenario. So just kind of keep that in mind. It's not the highest term only, because there could be an x term and a constant. And the only way that you can get that constant is to do the division. What about our intercept? So if I let x equal to 0, I get 0. And when the whole thing is equal to 0, then I also get 0. So the numerator being 0 will make the whole thing 0. So that is my other, both my x and my y intercepts are the same point. So let's try to sketch this and see, and then we'll compare to technology. So we have a vertical asymptote at -3. 1, 2, 3. And I have a horizontal asymptote at 1. The other thing that I know is I can find the value of my whole, is essentially my R reduced at 3, is going to be 3 over 3 plus 3, which is going to be 3 over 6, which is 1/2. So that will be a useful point to plot. So 1, 2, 3. It's going to be a hole here in the graph. Again, open circle because it's a hole. What else do I know? I know I have an intercept at 0, 0. So since I'm on this side of the graph, that's going to suggest that I'm going to coming up from infinity here and approaching my horizontal asymptote on this side. And then because this is not multiplicity 2, my sign has to flip on the other side and therefore has to come over this way. All right, so let's check Desmos and see how technology says. Now, one thing to kind of keep in mind is Desmos is not going to plot this hole, but when we try to find it on the graph, it is going to say that it's undefined. So let's see what we can do. X minus 3. All right, and so what do we end up with? We end up with this graph. So I've plotted in purple here the vertical asymptote so we can see it is approaching on either side. I've also plotted the horizontal asymptote in black here so that you can see, again, the graph in green is our function. It is approaching above and below. Here's our intercept. Now, Desmos, what it tried to do was it didn't plug in exactly 3. It plugged in something really close to 3. And you can see it's not, it's like 2.99999, and it's getting something very close to that 1/2, but not exactly 1/2. So it is identifying sort of that hole on the graph, but it's getting close to it rather than actually indicating. And again, if you just look at the graph without these points labeled, you won't be able to see on the graph that there is in fact anything going on at that point x equals 3, because it essentially, the whole graph looks like x over x plus 3, except for that hole. But when we draw it by hand, we have to draw it so that we can easily identify that there is a hole there. Again, technology won't always do that for us. And finally, there's so many other things that can happen. You can have multiple intercepts, multiple vertical asymptotes. Again, if they're not repeated, then they flip sign on the other side. You can have repeated roots in the denominator, in which case, again, that's going to behave somewhat differently. You can have oblique asymptotes where the numerator is a higher degree than the denominator, in which case you would have a diagonal line that you have to approach. But we're going to do one more example with the repeated root case, because we won't be able to cover every possible combination of things in a single video, unless the video was like 50 minutes long. X squared minus 4x plus 3 divided by x plus 1 squared. And of course, depending on how many factors you have, things can get quite weird. So since our numerator is not factored, we should try to factor x minus 4, no, x minus 3, x minus 1 over x plus 1 squared. So we have no holes. The domain is going to be all reals except -1. Because -1 is the only value that is problematic. We do have, let's see, the squared power on the bottom and the squared power on the top. So the vertical asymptote is x equals -1. The horizontal asymptote, if I multiply this out, I get x squared over x squared. I'm going to get y equals 1 again. Let's see about my y-intercept. When x is 0, I am going to get 3 over 1, which is 3. And if I set the whole thing equal to 0, then my numerator being equal to 0 will get me my x intercepts, which will be at x equals 3 and x equals 1. All right, so now let's try, again, plotting this, and then we'll compare to technology. So we know, for example, we had a horizontal asymptote at y equals 1, and we had a vertical asymptote at x equals -1, and we have some points we can plot. X equals 3, 1, 2, 3, and we have another one at 1. And let's see, do we have any other points? A y-intercept at 3, 1, 2, 3. All right, so now remember that inside the sort of large values, when you have small values, it is possible to cross horizontal asymptotes. And we have to, because we have to approach the intercept, we have to go through the intercept, but then we have to approach the horizontal asymptote. And there's no other zeros in here. So the only thing this can do is come this way and then go through our 0 and then go back through our other 0 and then approach our horizontal asymptote on this side. And then the thing that's tricky about this one is that our vertical asymptote is x plus 1 squared. So it's multiplicity 2. And that means if we check our sign chart, we should not be changing signs on either side of our asymptote. And so we're going to come back down from the top and then approach our horizontal asymptote on that side. The confirmation from that is also that if we were to flip over here to approach our asymptote, we'd have to go back through 0, and there are no other zeros over here for us to pass through. So we have to be on this side where there are no zeros. All right, so now let us double check with technology and see how we did. And so here's our Desmos graph. Here's our intercept. Again, notice it goes up to infinity next to our vertical asymptote. Here's our 0 intercept. Here's our +3 intercept. It does go down to a minimum. It's not very big, minimum, but goes down to a minimum and then back up, approaching our black horizontal asymptote here. And then over here, it's positive. It never goes through negative. The sign did not change as we crossed our vertical asymptote because it's x plus 1 squared in our denominator. And so that denominator never changes sign. So it might be undefined, it might get really small, but it's always positive. And so there is no sign change as we go through that point. So again, these are just some of the examples of plotting rational functions that you can encounter. There are so many more options. You could do multiplicities of 3. You could have higher degree polynomials. You could have oblique or even quadratic asymptotes, all kinds of things that can happen. But the idea here is always be methodical. Try to plot the vertical asymptotes, the holes, the horizontal asymptotes, plot intercepts, plot any kind of points you know. You may need to check 1 or 2 additional points just for reference. Keep track of the degree of your denominator, the degree of your zeros to know whether the asymptote flips sign as it crosses, the function changes sign as it crosses the asymptote or not, because again, it's going to depend on the multiplicity of the factor at that vertical asymptote. And then the crazy ones where there's no vertical asymptotes, you get a nice smooth function, but it's not like a polynomial or anything. It does have other kinds of asymptotes and things where you have to approach various values. So again, there's so many ways this can become so much more complicated, but this should give us a framework to get started with. And then most of these concepts you can apply to more complex problems. And perhaps we'll do some more complicated ones in other videos. But for now, this should get you started.